So what we are doing now is we have this time a sequence of numbers. We want to add all of them. Okay, so we have infinitely many of these things. We keep adding these things to each other. And we want to make sense out of this. Okay, so is this equal to anything? To anything. So that's the question. Of course, we don't have time to complete this sum. So typically what we do in science is we predict what the sum will be if we had enough time to add infinitely many of these terms. So what we do is we do this term by term. So we do this addition term by term. Okay, so we construct the sequence of partial sums. Okay, so first we add the first one. Okay, so this is A1. Then we add the second one, A1 plus A2. So notice that this is S1 plus the next term. Let's add the third one. This is A1 plus A2 plus A3. And again, notice that this is the previous sum plus one more term. Okay, so we go like this. Then we add the first n terms. And again, we notice that this is the previous one plus the last one. We keep going. Okay, so now we change the problem of adding infinitely many terms to considering this sequence. Okay, so this goes on like this. So we ask the question if this sequence has a limit. Okay, so does this sequence have a limit? Okay, so we agree that in the limit, in the hypothetical limit, we will have the limit is equal to infinite sum of all these things. Okay, so we agree on this. So if limit Sn as n goes to infinity exists and is equal to S, then we write A1 plus An plus this infinite sum is equal to S, or we shorten this, we say, okay, n equals 1 to infinity, An is equal to S, okay? And we say this infinite series An converges to S, or we say this sum is convergent. So most often, whether the series is convergent or not is more important because we don't always have an exact value for this. It is difficult to calculate the exact limit of these things. So you see, in order to calculate the exact limit of this, I must have an exact expression for this so that I can take the limit, but most of the time it is not easy. So we just check if the limit exists or not. Okay? If the limit exists, then the next question is how do we approximate this sum? Sometimes we can't find the exact value. Even if you know the exact value, when in practice you are doing an approximation. So suppose the limit is pi. Okay, it is exactly pi, but when you are going to use it, you use 3 or 3.14, etc. So that's an approximation. Okay, so that's the second stage. The first stage is whether this is convergent or not. And the terminology is when it is not convergent, we say it is divergent. Okay, so if limit Sn n goes to infinity does not exist, Remember that does not exist includes includes the case when limit Sn is infinite. Okay, so then the limit does not exist. We say summation an is divergent, or we say, or it doesn't exist. Okay, so this part is just terminology. When we know the limit of the sequence of partial sums exists, we say that this infinite sum exists. It is convergent. It is convergent to that limit. Okay, so this is the terminology. Okay, so the first, after you make such a definition, the first thing is there an occurrence of this? Okay, you can always make the definition of a black living creature walking on 3 legs and having 1 wing. Okay, that's a perfectly good definition. We can call it alpha 0, but there exists no alpha 0. Okay, so we have to check if an infinite sum exists. The first thing we know is the geometric series. So let us start with this. So first question is there a convergent infinite sum? Okay. Consider the geometric series. Okay, I'll skip the constant. Generally in the books you have constants here. You keep multiplying all of them by constant, but okay, we are not stupid. So if we see a constant, we take it out. Rn plus. Okay, so is this going to add up to anything? The easiest way to see this is to look at the following. You have 1 plus r plus rn for a fixed n. Okay, so suppose r is different than 1. Okay, so if r is equal to 1, I keep adding numbers. It will go to infinity. It's clear. So I look at the case when r is different than 1. Then I multiply this by 1 minus r. Okay, so this is where, algebraically, this is where I need r different than 1. So I'm multiplying this by something not 0. Okay, so if you multiply this, you will see that. Okay, so let me write this. First, you multiply this by r. By 1, you get r to the n. Then you multiply everything by minus r. So you start from here. You have minus r squared minus rn, and you multiply this minus rn plus 1. Okay, so when you write this, this is 1 minus rn plus 1. I'm interested in this part. So observe that this is the nth term of the sequence of partial sums for my infinite series. So Sn is equal to 1 minus rn plus 1 over 1 minus r. Okay, now I want to take the limit of this. Okay, let me take the limit here. Limit Sn as n goes to infinity is equal to limit of this side. Here n appears only here, so this is 1 minus limit n goes to infinity r n plus 1 over 1 minus r. Okay, so this limit exists if and only if this limit exists. Okay, so we have here. But we know that this limit exists if and only if the absolute value of r is less than 1. Okay, so that's what we did last week on sequences. Okay, so limit as n goes to infinity r n plus 1 is equal to 0 if and only if absolute value of r is strictly less than 1. Otherwise, the limit does not exist. Okay, so now we put that here. Hence, limit of the sequence of partial sums as n goes to infinity is equal to 1 over 1 minus r if the absolute value of r is strictly less than 1 and the series diverges if absolute value of r is larger than or equal to 1. Okay, so there are infinite sums which add up to a finite number. The next thing to do is to go back to here and extract an extra information from here. Okay, so so next, consider Sn equals Sn minus 1 plus An. Okay, so assume limit Sn as n goes to infinite exists and is equal to the real number s. Okay, so suppose we have a convergent infinite sum. Okay, so we know that they exist. At this point, we don't know if anything other than geometric series exists, but if it exists, what are the consequences? Okay, then we take this here, limit Sn as n goes to infinity of limit, and this is equal to the limit of the right-hand side of Sn minus 1 plus An. I'm assuming that the limit is s, so remember that this side is, that's why we have these silly theorems, but we can use them with confidence. Okay, so if the limit exists, this means that s is equal to, so this is again s plus this I don't know. Okay, so from here it turns out that this is 0. So limit An at n goes to infinite is 0. Okay, so with this assumption we came to this thing. Okay, so if that is, if summation An converges, then the general term goes to 0. Okay, so with this, in this way, this is useless because we are trying to understand this. I want to know if this converges or not, and you are telling me something that will happen after this converges. When this converges, all my questions are answered. But when we turn this around, it becomes a very crucial information for us. When this thing doesn't hold, then this is not convergent. Okay, so this is one of the major theorems in series. This is called the nth term test. Nth term test. So this is generally abbreviated like this in this course. Okay, so in the exams maybe you may be asked to show something converges or diverges, and of course you have to explain. So if you are using this test, you can, instead of writing all of this, you can write this. Nth term test. This says if limit An as n goes to infinity is not 0, then summation An diverges. Okay, so now that's very useful. At least now I have a way of recognizing some of the divergent series. Okay, so this doesn't say that if the general term goes to 0, the series converges. It doesn't say that. Okay, because in order to apply a theorem, you have a premise, you have a condition, and you try to check if the condition, this condition agrees with the condition of the theorem. Okay, suppose you have summation limit of the general term, limit An goes to 0. Okay, this is our condition. Does it fit here? No, this says it's different than 0. Does it fit here? No, this says if the sequence converges. Okay, so if the limit An goes to 0, it doesn't fit to the premise of any theorem. Which means that if you calculate and find out that the limit of the general term goes to 0, you did not learn anything. Okay, you don't know anything about the series except that its general term goes to 0, which means that now you have to continue to work. Okay, so this is very obvious in real life, but in the exam, well, exam is not real life, so you are free to write whatever you like in the exam, but always there will be a dozen people or 2 dozen people who will check the general term. The general term goes to 0, and they say, who cares, let the series go, converge. Okay, it doesn't. It may or it may not converge. If the general term goes to 0, we learn absolutely nothing about the series. The series may converge, may diverge. We'll have lots of information where the general term goes to 0 and the series diverges or converges. Okay? So, but this part is very important because we will learn very fascinating tests to check if a series converges or not. And once you understand how these tests work, you are, of course, tempted to apply them. Sometimes you apply a test to a series, you break your back, you do lots of calculation, and finally you find out that the series diverges. Okay, so somebody points out that if you had checked the general term, it was obvious that the general term was not going to 0. So you could get the same result very easily. Okay, so that's why this is the first thing that you check when you are trying to find out if a series converges or diverges. You check this. If the general term does not go to 0, you are done. If the general term goes to 0, okay, now you continue. You can apply all your fancy tests to check if it converges or not. Okay? So another note is, what does this mean? Okay? So this means limit an as n goes to infinity is equal to a number, but this number is not 0, or limit an as n goes to infinity does not exist. Okay, so one way or the other. Both of them are included here because you see this is the negation of this sentence. Limit an equals to 0, and we are trying to look at cases outside this. Cases outside this are these things. The limit exists, but it is not the 0 number, or the limit does not exist. Okay, so with this in mind, let us look at one of the very famous series. Okay, so this has been a very interesting case. Now consider the series summation n. Okay, let me start from 0 minus 1 n. Okay, so this is my series. Okay, so you see that this is 1, minus 1, plus 1, minus 1, plus 1. This goes on like this, and the general term is minus 1 to the power n. Okay, here an is equal to minus 1 n. I immediately check this. Limit an as n goes to infinity does not exist. Okay, so this sequence oscillates between plus 1 and minus 1. The limit does not go anywhere. Okay, so the series diverges. Summation an diverges. Okay, now we totally understand that this series does not add up to anywhere. Okay, but we are tempted to do the following. Okay, so summation an is equal to 1 minus 1 plus 1 minus 1 plus 1. Okay, so I'll write a few more of these things. Okay, let me take this, 1 minus 1 plus, so this goes on like this. And I'll also have plus 1 minus 1 plus 1 like this. So I put parentheses like this. Okay, so you see that this becomes 0, 0, 0. Now, whatever theory of infinite series you develop, this must be 0. Okay. Now I do the following here. I put parentheses like this and this. Okay. So this is 1 plus 0 plus 0 plus 0. So again, this must be 1. Okay. So we found that we did not find that 0 equals 1. We find 0 equals 1 under a condition. The condition is that if we are allowed to regroup these things in any way we like, then 0 will be equal to 1. Okay, so it speaks for itself. It tells that You are not allowed to do these things. In mathematics, when we say you are not allowed to do this, it doesn't mean that police will interrupt you if you do this. You are free to do this, but the result you get will not be valid. Okay, so that's what we mean, you can't do this. So if we have an infinite sum, you cannot put parentheses like this. There are conditions under which you can put parentheses and get the same result that we will do later. Okay, so I can tell you at this point, but if the series is such that if you take the absolute value of a_n's and add them, instead of adding a_n's, some of them will be plus, some of them will be minus in general. But if you take the absolute value of all of them and add, and you get a finite sum, okay, if that is the case, now you can go back to your series and you can put parentheses in any way you like, and you'll always get the same answer. In fact, more interesting things happen. If the series converges, suppose it has pluses and minuses. For example, what I'm saying now does not apply to this because this doesn't converge. Suppose the general term goes to 0 and there are other tests. We find out that the series converges. Okay? And then you also check that if you put the absolute values, the series with the absolute values also converges. Okay? So this, okay, we'll do this later. This is one of the best situations. In this situation, you can put parentheses in anywhere you like, and you'll get the same result. But if the second part doesn't hold, if you put absolute values, it diverges. You don't have a sum. But after you put pluses and minuses, it converges. Then you can choose a number in your mind, and you can put pluses or you can put these parentheses in any way you like, and you can make a series which converges to the number you like. So that's how chaotic it will be. But we will do this in detail after we do, I think we'll do this next week. So this week, basically, we'll be talking about series with positive terms. Okay. So next week, we will start with series which also have some negative terms in it. Okay. So they are more interesting. But when the series have negative terms in it, we don't have many tests to check if it converges or not. Almost all of our tests apply to the case when the general term is positive. So what we will do there is we'll look at the absolute values. If it converges, then we are done. Or if the terms alternate like this, then if a few more conditions hold, it will converge. But if you have a series where you cannot see any pattern in pluses or minuses, you look at the absolute values, it doesn't converge, then we don't have any way of telling whether the series converges or diverges. Okay, this is to teach you some modesty. Okay, so the conclusion of this is going back to what we learned. We definitely know that the series diverges, and we definitely know that these two numbers are not the same, so you cannot put parentheses. Okay, so moral of the story. You cannot regroup infinitely many terms. Let me say in general, because next week we will see under which condition you can do this. You are tempted to put these parentheses because you see it's very easy here. Now I immediately obtain an answer. Okay? So we want to know when putting parentheses are allowed. So we'll do that next week. And okay, the general thing is if you know the series converges, and if you know the series with absolute values converges, then you can do this. But in our case, neither converges. Okay, so this is one thing. Another very famous series is a striking counterexample to what you feel. What a wonderful world it would be if a series converges if and only if the general term goes to 0. Fortunately, there are such worlds. If you look up non-Archimedean analysis, what we are doing here is all Archimedean analysis. Okay, so it's about what you understand in the plane, if you have the triangle inequality, etc. In non-Archimedean analysis, the numbers behave differently, and an infinite series converges if and only if the general term goes to 0. But since calculus is Archimedean, that doesn't hold here. So here is a counterexample. Okay, so another famous example. So this was very famous. You might understand this because you see you are doing this, you get 0. You are doing this, you get 1. What you are doing sounds very reasonable. Before we started to understand the general behavior of infinite sums, you are perplexed here. Okay, we know that we are doing something wrong here, but why is it wrong? Okay, so we come to this understanding after we totally understand series, then we go back and explain this. But until it was explained, it was of course a debate. Okay, another thing is this one. This is there was no debate about this, but people are very, very surprised. Consider the series summation n equals from 1 to infinity 1 over n. Okay, so it looks very nice. You write it like this. 1 over n. Okay, so this is very famous. It even has a name. Its name is harmonic series. So why do you give a name to something in mathematics? Because it pops up here and there unexpectedly. So you decide to give a short name to it every time it appears instead of describing it all the time. So this is very surprisingly pops up everywhere in calculations. The general term obviously goes to 0. We are adding smaller and smaller terms to this. Okay, so the general expectation is that it will converge. And of course, now that we have computers, we rush to the computer. You write a program, a loop without any stopping. Okay, so say, give me 12 digits and start calculating this 1 over n's. Okay, take floating. If you don't say anything, the poor computer will calculate this as a fraction. You add another 1 over n plus 1, it will calculate as a fraction, so you don't understand anything. So you say just do this floating point so that you get 1 point something. Okay, in the first you have 1, then you have 1.5, etc. Okay, if you sit there a few minutes, you will see that eventually the numbers on the screen stabilizes. You start seeing the same number. Okay, depending on the speed of your computer, this may take 5 minutes or 6 minutes, whatever. Okay, so then your conclusion is that the limit is whatever you see there. Maybe you see 12 there. Okay, somebody has a better computer. If he decides to use a little bit more digits, then maybe he'll see 15. Okay, so whatever experiment you do, the limit of this thing is final. Okay, all empirical data tells you that this is going to add up to some number. Okay, there is even an exercise in old books. I don't know why they canceled it in the new books. Suppose you are using the fastest computer. I think the fastest computer nowadays is doing 93 floating point, 93 times 10 to the 15 operations per second. Okay, so suppose at the beginning of Big Bang, somebody invented this computer and started to add these things. So in 1 second, he adds from 1 to 10 to the 15, 93 times 10 to the 15. Okay, and then the next second it adds anything. So, and he keeps doing this for the 13 billion years since Big Bang. Okay, so again, experimentally, he will see that the number is 79 point something. It's not even 80. Okay, so there's absolutely no empirical evidence which will suggest you that this thing diverges. But it is divergent. Okay, so the only way to see that it diverges is, of course, to apply something, to analyze it. Okay, so Sn is the following thing: 1 plus 1 over 2 plus 1 over 3. Okay, I'll do it this way. 1 over 4 plus 1 over 5 plus 1 over 6 plus 7, 1 over 8. And then I have 1 over 9 plus nereye kadar gidecek? 1 over 16 plus like this, okay? So you see, we look at this one now, okay? I'm looking at partial sums. So this one is, I want to look at this one. Okay, so this is 1, this is 1 over 2. This is larger than 1 over 4, okay? So this whole thing is larger than 1 over 2, okay? So now I look at this thing. This is larger than 1 over 8. This is larger than 1 over 8, larger than 1 over 8, equals to 1 over 8. So you have four terms which are larger than or equal to 1 over 8. So the whole thing is larger than 1 over 2. Okay, so you see that's the pattern. This is larger than 1 over 2. Okay, so you go 1 over 2 to the power n minus 1 plus 1. Okay, so this plus 1. You keep adding these and you go up 1 over 2 to the power n. So each of them is less than 1 over 2 to the n. Okay, and you have 2 to the n of these things. So this whole thing is 2 to the n minus 1 of these things. So how many of these? So this whole thing is, again, this is larger than 1 over 2. Okay? So you see that, of course, these numbers are very large now. After this, you add a huge many numbers. And what you added is slightly larger than 1 over 2. And then you add even much more many numbers, but they add up to something slightly more than 1 over 2. So you are adding terms larger than 1 over 2 infinitely many times. So this thing goes to infinity. The formal way to do this is the following. S2 is equal to 1 over 2. S2 to the power, S2, these are partial sums, okay? So this is S4, adding up to S4. So this is larger than 1 plus 1 over 2. So S2 is, okay, this is 1 plus 1 over 2. This is 1 plus 1 over 2 plus 1 over 2. Okay, so how many 2's I have? This many. So S8 is S2 to the power 3 larger than this. And I have this. Okay, so plus 1 over 2. So this is 1 plus 3, 1 over 2. So by induction, you can show that so that's, you have to calculate this. 2 to the power n is larger than 1 plus n to the 1 over 2. Okay, so limit S2 to the power n as n goes to infinite is equal to infinite. Okay, so this is a subsequence of the sequence of partial sums. A subsequence goes to infinity, so the sequence itself is divergent. Okay, so therefore, so remember that this is what goes through our mind. S2n is, okay, so if you want this formal, you put parentheses here, etc. But in this class, I'm using this as a shorthand. So this is a subsequence of the sequence Sn. So this is A1 plus, well, in our case, we know exactly what this is. 1 plus 1n, okay? A subsequence is divergent. So limit Sn as n goes to infinity does not exist. Actually, it is infinite for extra information. Since there are no negative terms, it's not fluctuating. Every time you are adding something, and if you add enough many terms, you have added something slightly larger than 1 over 2. So you keep doing this. So this famous series where the general term goes to 0, no Note, however, an is equal to 1 over n goes to 0 as n goes to infinite. Okay, so the general term going to 0 in the geometric series comes with the convergence series. Here, it comes with the divergence series. Okay, so you should always see these tests as something coming out of a black box. Okay, so what you see, you have the general term going to 0. So inside the box, which series could have sent it to you? Okay, so now we know that a divergence series can send you this, and the convergence series can send you this. So if you only look at the general term and it goes to 0, you can't tell what was in the black box. But there's a sequence in the black box which sends you a general term which doesn't go to 0. So now you can immediately know that inside the box there was a divergence series. Okay? Okay, so these are the two famous series. What will be also interesting is when next week we'll put minuses here, 1 plus 1 minus, 1 plus 1 minus, 1 plus 1 minus, and surprisingly that will be convergent. And in fact, we will know exactly what its value is. It will be ln2. Okay, so we have this. Another thing I think we can do this. Another thing we know from high school is repeating decimals. We know that if you have a decimal expansion, and after a while the decimal a pattern in the decimal expansion repeats, then we were told in high school that this is always a rational number. Okay, so let's check that. Repeating patterns in decimal expansions. Okay, so for example, let's say C is a number which is, let's say 0.21111 something. I'm just inventing this. So in high school, they told us that we can write it like this. You put a bar. If a pattern is repeating, you put a bar there. Okay, so claim this is C is a rational number. Okay, so we check that. So C is, so we write C as an infinite sum. So C is equal to 0.2. Okay, I'll write this as 2 over 10 in a minute, plus, okay, so let me write it 2 over 10, the minute has passed. Okay, so this is 2 over 10, plus, so this is 1 over 100, okay, 1 over 100, plus 1 over 1000, plus, so it goes on like this. We see that there's a geometric series here, so let's make that very apparent. 2 over 10 plus 1 over 100 times 1 plus 1 over 10 plus 1 over 10 squared plus something like this. Okay, so am I writing this correctly? Okay, so this part, this is a geometric series. Geometric series with general term equals 1 over 10, which is less than 1, positive less than 1, so it converges. So this thing is equal to 2 plus 10 plus 1 over 100 times 1 over 1 minus 1 over 10. Okay, so it's a rational number, which is a rational number. Okay, so this shows us that no matter which pattern we have here, instead of having just one thing, you may have, I think the largest one is you have, no, in reciprocals, the largest one is 7, but in general, you can write here a huge sequence and then repeat that. Okay, so eventually it will be like this. Okay, so instead of 1 over 100, here you'll have a number, your pattern, divided by 10 to something suitable. Okay, and then every time you take the square of this or multiply it by something, so it keeps like this. You take out some common factor, your pattern will be here, and here you'll have a clean geometric series. And you know its general term is like this. Since the general term is a rational number, this is going to be a rational number. These things are rational, so it will be a rational number. We also have the following repeating pattern. If 9 repeats, okay, so you have a difficult time trying to explain to your friends who are not in engineering that this is the same. Note, however, 1 is 0.9999. Okay? So there are several ways of proving that these two things are the same. This is not surprising because there is the number 1 in the concept 1, and how do we represent it? You can write 1 in English that represents this. In Turkish you write 1 that also represents, but the Turkish word and the English word are different. Okay, so nobody will tell you that these are different, so they should represent a different number. Okay, so this is the same thing. Okay, these are different symbols, but they represent the same number. An easy way to see it is to call this 0.99 something x, multiply x by 10, and then show that it's, okay, then it is 9 plus x. Okay, then there you can see that x is equal to 1. We want to do this now by by infinite sums. This is equal to 9 over 10 plus 9 over 10 squared plus 9 over 10 cubed plus, okay, so I can take 9 over 10 out, and here I have 1 plus 1 over 10. Okay, so 1 over 10 cubed plus this goes like 1 over 10 n plus this. This is a geometric series, 9 over 10. This is 1 over 1 minus 1 over 10. Okay, so you see that this is this part is 10 over 9. This is 9 over 10. This is 10 over 9. So this is equal to 1. Okay, so this reminds us that every real decimal expansion ending in zeros can also be written as ending in nines. Okay, so you just subtract the previous integer, make it smaller, and instead of zeros, now you put everything 9. So those two representations are different representations of the same number. Okay, so you also had this. Okay, so maybe I finish with this one. Okay, another series that we can calculate explicitly is known as telescoping series. Okay, so telescoping series. Theoretically, this is not very important because next hour we'll find the general theorem which says that, or maybe next hour this week, that telescopic series are convergent. Okay. The reason why we call them telescoping is using partial fractions we can write them in such a way that the sums collapse and you get a general expression for Sn. Once you have an expression for Sn, you can find explicitly what the sum is. Okay, so theoretically these are not important, but practically these are the second type of infinite series besides geometric series whose sum you can explicitly calculate if you are lucky. Okay, because if the general term becomes large, theoretically we know that there is a way to do it, but practically you break your back to do it. Okay, so here it is. Let's do one example. Summation n equals 1 to infinity. I think I'll use, okay, the book uses n times n plus 1. I'll use n plus 2. I'm putting this 2 here because in a minute I'll have 1 over 2s. I don't want to carry 1 over 2s around. Okay, so here we'll look at the general term an. So this is 2 over and n plus 2. I want to write it using this partial fractions, whatever, n plus b over n plus 2. Okay, so when you do this, this is a plus b n plus 2a and n plus 2. Okay, so that's why I wanted to have this 2. If I have 1 here, then 2a is equal to 1. A is 1 over 2. So instead of carrying 1 over 2's around, 2a is equal to 2, and a plus b is equal to 0, because the coefficient of n on this side is 0. Okay, so from here I know that a equals 1, b is equal to minus 1. So an is equal to 1 over n minus 1 over n plus 2. Okay, next we write Sn. Sn is equal to a1 plus a2. I'll write them one under the other. A1 is equal to 1 over 1 minus 1 over 3. A2 is 1 over 2 minus 1 over 5, 1 over 4. Okay, 1 over 4. Plus A3, 1 over 3 plus 1 over 5. Let me write one more here, 1 over 4 minus 1 over 6. Then I'll have lots of things. So the last thing I'll have will be 1 over n minus 1 over n plus 2. Okay, let's see here. I'll have also here plus 1 over n minus 1 minus 1 over n plus 1. Let me write one more here, plus 1 over n minus 2 plus minus 1 over n. And then I have dot, dot, dot here. Okay, so now we can cancel. Okay, so this is the name. This is where the name comes. This thing telescopes down to a few terms. Okay, so 1 over 3 cancels here. 1 over 4 cancels here. So we see that something here, it moves like the knight in chess, goes down and cancels this one. It goes down 2 and cancels this. This goes down 2 and cancels this. This will be canceled. This will be canceled. So these two guys will not be canceled. And here, you see this will be canceled by this. Okay, so this will be canceled by this. There is something. These will be canceled. So these are the only things which are not canceled. This is not canceled. This is not canceled. And these things are not canceled. Okay, so we know that this thing is now, so Sn is equal to 1 plus 1 over 2. So this is 3 over 2 minus 1 over n plus 1 minus 1 over n plus 2. Okay, what am I interested in? I'm interested in limit Sn as n goes to infinite. Okay, so this is going to be a very typical case. You will have some numbers here which are not cancelled, because there are the things that we are going to cancel according to this pattern would be here, but there's nothing here. And since everybody cancels something down, these guys are not going to cancel anything on this side. And they are always 1 over n plus something. So they go to 0. Okay, so 3 over 2. Okay, hence, summation n equals 1 to infinity, 2 over n plus 2 is equal to 3 over 2. You see, this is when is it going to be difficult? Instead of having 2 terms here, if I have 5 or 6 terms, then here you have to solve a linear system of 5 unknowns in 5 equations, which is again theoretically totally understood, but practically it takes a lot of time to solve such systems. Okay, so it's very time consuming, but the theory is totally understood. And of course, once you manage to do that, instead of having a square here, I can have 5 terms, say. Then here you will have 5 terms. Here you will have 5 terms, and for each of them there will be a different pattern of cancellation. And again, the same thing will hold. All these guys are going to cancel things on the left-hand side. Okay, there will be a block here which is not cancelled. And there will be a block here, not cancelled, but the block here will be always of the form 1 over n something. Each of them will go to 0, so the sum of this block will be the limit of the telescoping sum. Okay, let's stop here, take a break, and then we'll add some more terms next hour.